I'm Chris Moody. I'm a graduate student here. I'm working with Joel Premack and that list of collaborators, almost all of whom are actually in this room right now. And what I want to talk to you today about are how we're finding fewer small clumps in these simulations, this newest generation of simulations, once we do add radiation pressure feedback. All right, so the starting point is a series of simulations by Daniele Severino. He's using the ART code. They're not isolated simulations. They're conducted in a fully cosmological box. They have all the major and the minor mergers that's associated with. But what's nice is that they have really high resolution. They're about 17 parsecs. And we also have about 15, at the moment, identical pairs of simulations. And the only difference between them is that some have radiation pressure turned on and some of them have it turned off. Otherwise, the way the galaxy forms is completely identical. You have the same major mergers, you have the same dark matter background, or backbone, and you have the same formation history. The simulations are around 10 to 11, 10 to the 12 halo mass, which means 1 to 3% of that mass is in stars, so their stellar mass is something like 10 to the 9, 10 to the 10 in stellar masses. One more thing I want to say is that radiation pressure has a tau of about 1 to 2. So that's how we're implementing our feedback. And most of these simulations are conducted all the way down to redshift of 1. So why do we care about radiation pressure feedback to begin with? And so historically, the simulations have been producing too many stars too quickly, too early on. So radiation pressure feedback is a nice way to sort of try and depress the amount of stars that we're forming. And so that's exactly what this plot is showing. So on the bottom axis, you have halo mass. And on the y-axis, you have m star over halo mass, so the fraction of that halo mass that's in the form of stars. Blue points are simulations without radiation pressure. So they're blue, they form more stars. And then the red points are with radiation pressure. And so that actually reduces the number of stars by a factor of 3, or the mass of stars by a factor of 3. And the line there are the Peter Peruzzi, Conroy, and Wexler data that show what you might expect for a given halo mass, how much of that mass should be in the form of stars. So the way to read this is that at 10 to the 12 halo mass at Z of 1.5, that's the right panel, and then the left panel, the left panel is going to be a Z of 3. At Z of 1.5, you expect a 10 to the 12 halo mass to have about 2% of its mass in the form of stars, and so that's the peak. So you might look at this and naively, as I have, think that, well, we're producing we're getting pretty close at Z of 1.5, and you might still want a little bit more feedback to try and match that line. And at Z of 3, you probably still want even more feedback. You can sort of try and extrapolate that line out. So the moral of the story is that maybe you might actually want a little bit more feedback from this. Just, order of magnitude from here. All right, so that's what's happening globally. Let's look at what's happening visually and morphologically and qualitatively. So I thought this was striking the first time I saw this. So this is one simulation, VELA 13, and you're looking at the projected stellar column density. And the left panel is the simulations without radiation pressure, and the right panel is the ones with radiation pressure. So what you see are that there are far more clumps found in the ones without radiation pressure. So the clumps are circled. We're using a really simple contour finding clump finder per se. And then the red squares are clumps that are found in the dark matter as well. So we run the Rockstar Halo Finder on it, and then we throw those guys out. We just call them ex situs. For the rest of this analysis, we're just going to talk about the in situs. So just what to say here is that yes, that radiation pressure simulations are actually lacking in the small number of clumps. We can't tell the difference between whether these clumps are prevented from ever being formed or they're simply disrupted really quickly. So we're not following the history of each clump. All we know are the instantaneous clump counts. All right, so that was qualitatively. So hopefully that gave you an intuition for these clumps are actually disappearing. Let me try to quantify that in some way. And what's shown here is the number of clumps per galaxy as a function of time. So the number of clumps is on the y-axis, the x-axis is scale factor, and also redshift going from 4 to 1. And the median, and so what you see is that for the no RP simulations, the median number of clumps is climbing. It climbs up to about 3, and then it falls after Z of 1.5. But there's a huge huge dispersion in this relationship too. So those aren't error bars. Those are actually representing the distribution of the numbers of clumps. So the way to read this is that at z of 1.5, you can have a simulation that you can find a quarter of your snapshots in the no RP simulations have more than 8 clumps in them. So these simulations are really, really, really pretty clumpy. Now that changes dramatically as soon as you add radiation pressure. All of those red points are along the 0 line. So the median number of clumps is 0 once you add radiation pressure feedback. So your average snapshot doesn't have a clump in it. Okay, so the story gets more interesting from there. So let's sort of try and differentiate between clumps that are big and clumps that are small. And the way we're going to do this is by taking the clump mass and normalizing it to the mass of the disk. So that's exactly what the x-axis is here. So you have the clump mass divided by the mass of the disk. And so blue, again, is no RP. Red is with radiation pressure. And you see what I've been telling you for the last few slides, that when you have no radiation pressure, you have dramatically more clumps. But what's interesting is that once you get to about 8% of the disk mass, these clumps are preserved. So the clump counts are equal here. So while most clumps below that mass are gone in the radiation pressure simulations, most of them are maintaining their clump counts above around the 8% cutoff. So there's a big difference between small clumps and big clumps. Just to throw some numbers out, if the halo mass is about 2 times 10 to the 11, the baryon or the stellar mass is about 1 to 3% of that, so you have something like a 1 times 10 to the 10 in stars, and then 8% of that again, you have about 10 to the 9. So these giant clumps are around 10 to the 9 in solar masses, including the total baryons, all of the baryons. Okay, so let's look at the growth of the total mass of clumps in a galaxy. So in this case, remember that the radiation pressure simulations, most of them didn't have any clumps at all. So in this case, I've had to select just the clumpy galaxies. By picking just the galaxies that are hosting at least one giant clump. So there's a selection going into here. So that means that I've thrown out the majority of the snapshots for the radiation pressure case, but that's okay. We're being careful about only picking the clumpy galaxies and constructing. So the takeaway here is that the trends are roughly similar between the radiation pressure and no radiation pressure cases. They still peak at about z of 1.5 and declining afterwards. And this actually, I think, mirrors the number of clumps plot. So I think this makes quite a bit of sense. And maybe the only other thing to take away from this plot is that the radiation pressure simulations, that their masses are still being depressed by a factor of 2 or 3, and that makes sense because that's the overall effect of the radiation pressure feedback. All right, so let's look at the homogeneity of these clumps by measuring the contrast ratio. So the x-axis here is going to show that normalized clump mass again, and it's a log-log axis here. And then blue points are, as before, without radiation pressure, and then red points are with radiation pressure. And so the contrast ratio, the way it's defined here is that this contour finding, this clump finding, is going to give you a region around each and every clump. And that region's going to have some number of pixels inside of it. So the contrast ratios, what we would like to have is the peak clump density divided by something like the disk density. So the way I'm doing this here is by taking the 95th most dense pixel and dividing it by the 5th most dense pixel. So that should be something like the peak of the peak density divided by the circumferential density. So divided by the density of the local neighborhood of the clump. So that's how this contrast ratio is being defined. So without radiation pressure, your contrast ratios are pretty high, and they stay pretty high with climbing clump mass. And there's a big difference between massive giant clumps in the radiation pressure simulations and not massive small clumps in the radiation pressure simulations. Those are the red points. For big clumps, the contrast ratios start to look pretty similar. They're still a little bit lower. But for the small clumps, these are really diffuse. They're not peaky at all. They're only factors of 2 or 3, not even, above the overall disk density. So they're really, really homogeneous, whereas the radiation pressure simulations, you have clumps. They're really peaky, really heterogeneous. Okay, so I think that's actually everything I wanted to say here. Maybe I guess I ended a little bit fast. But I'll recap by saying that the radiation pressure is reducing, or global effect, by reducing m star by a factor of 3. And just if you want to believe the Baruzzi data, you want to reduce that further. You probably think that you need to add more feedback. But the effect of adding that feedback is that you've removed some of the smaller clumps. And small here is being defined as about 8% of the disk mass. Now we don't know whether these small clumps, whether they never form or whether they do form and they're just disrupted really quickly, and so they have really short lifetimes. All we know is the instantaneous clump counts are the same at the high mass end of the clump masses. So, so the trends in clump number, in mass, and in contrast are similar as long as you look at the high mass clumps. And as soon as you go to the low mass clumps, radiation pressure really starts to kick in and have an effect. And then just a plug for future stuff. We want to test the observability of these clumps by looking at sunrise simulations. We're working with Yiqing Guo on that and trying to see whether these clumps are actually observable. All right, thank you.
Okay, any questions? Yeah.
So you were talking a lot about how your radiative pressure feedback sort of separation by a factor of 3.
Yeah, roughly speaking, yeah.
Yeah, but then you're still off by a factor of 3, and you say, well, if you want to add more feedback, so what feedback do you need to add? I mean, like, what other feedback do you need to add?
I mean, you could always, try and implement blast wave feedback if you want. I think that's what we're going to go with that, right, Daniel? Maybe. That's an alternative, but I don't know if that's also going to affect the small clumps. I don't know if you keep cranking up the radiation pressure feedback. Does that mean that 8% line is that going to push that up or down? So I think these are all still questions that need to be answered as you start to increase feedback, or if you change the feedback prescription too. I mean, these clumps exist in real life, so it's important that you keep at least some of them. And it's important that you also match that Baruzzi line, so you have to balance those two.